Okay, so 4 divided by 6. I can reduce it by taking a 2 out. Divide by 2, divide by 2, and I'm left with 2 over 3. If I have an x squared over x, that's technically just x times x over x. Can I take out 2 for 1, like bam, bam, and take that one out too, because I really want to? No, it's a 1 for 1 deal. So I can take one of these out for one of these. So I'm left with x. The same thing here. I can take one of these x's off for one of these x's, and I'm still left with just x. So same rule here. Sine squared theta divided by sine theta. Follows the exact same rule as the last one. I can take one sine off for one, and I'm left with sine theta. So remember, all of these sines and trigs just follow basic polynomial rules. So you need to just imagine it as x's or y's if you have to. Okay? Like I could imagine this sine squared as x squared over x and just treat all sines as thetas as x. So okay, that would reduce and I'd be left with an x. Okay, well x is sine theta, so then it's just sine theta. Now, in grade 10, this gets people too. If I had like x plus 2, so what they'll do is they'll cross off all the x's. The moment anything is in brackets and attached by a plus or minus sign, plus or minus signs attaching something is like it's sewn together. The plus or the minus sign is like the stitching. It's like the stuff is sewn together. So this x plus 2 is sewn together. That is one term. This x minus 3 is sewn together. It is one term. This x plus 2 is one term. So the only way that anything that's attached by plus or minus signs is going away if it's on the top and the bottom is if it's an actual twin to it. It has to be exactly the same. So this is like the head, the feet, the body. Okay, this is like a twin. These two match. This one is not a twin. It just has a head that looks similar to the other one, but it's not a twin. You're not crossing it off. You're like killing people if you're decapitating them. You are taking their heads, and you are left with numbers, and you're mean. So don't do that. We don't want any killing. It's Canada. So x plus 2's cancel, and we're left with x plus 3. So this one here, I have a 1 plus cos x. The only way that 1 plus cos x is going anywhere is if I have a 1 plus cos x on the bottom. Do I? No, so that baby's staying for life. Then I have a sine x and a sine squared x. Can I cancel those off? What? Can I cancel off all of it? Just one sine for a sine, right? Sine squared x is like having a sine x times a sine x, remember? So it's like 1 for 1. So then I'm left with 1 plus cos x over sine x. This one I have a 1 plus sine x and a 1 plus sine x, so those can go away. Remember, if I state restrictions, if they ask me for restrictions on the test, I always have to state them before I cancel, just like with rationals. And I'm left with cos x over sine x. What is cos x over sine x? It's on your formula sheet. Cotan. So this is like saying sine x over 1 times cos x over sine x. Because anything that doesn't have a denominator, the denominator is just 1. So what could I do? Cross off the sine x's and left with cos x over 1, or just cos x. H. What could I do? This cos x minus sine x is attached by plus or minus sign, so I can attach them by putting brackets around them, right? By putting brackets around them, I'm showing that they're actually attached to each other. And then the sine x is by itself and the cos x is by itself. Because there's a multiplication sign, anything that's in the top in the numerator somewhere can cancel off anything that's exact same in the denominator. So this can cancel this. So I'm left with sine x over cos x, which is tan. So remember, if I have 2 plus 3 over 2 plus 4, can I just cross those 2's off? No, because this would be 5 over 6, which is not 3/4. So remember, if they're attached by plus or minus signs, they're attached. You can't just cross one off. So we're not going to do number 4a, but we're just going to remember, if we have those radicals in the denominator, we'd multiply by the conjugate, right? Because we want to rationalize the denominator, which means we want to get rid of the radicals. So instead of we're multiplying by root 3 minus 2, which would just get us a middle term with a root and wouldn't fix the issue, we would multiply by the conjugate, which is root 3 plus root 2, right? In proofs, you're only going to do this for ones that can get you trig identities. So your trig identities are these ones at the top. They're those Pythagorean theorem ones. So sine squared x plus cos squared x equals 1, or 1 plus tan squared equals secant squared, or 1 plus cos squared equals cosecant squared. The only ones that work are the ones that get you a minus sign. So whenever I see a 1 minus cos or a 1 minus sine, and I see it somewhere, some people would look at this and they'll be like, there is absolutely nothing I can do with this. Okay? I can't change sines and singular sines and singular coses into anything, right? They're just sines and coses. I can change secants or cosecants or cotans or tans, but sine and cos are the bare minimum I can go. So whenever you see a 1 minus cos or a 1 minus sine, this should happen. So when you see a 1 minus cos x or a 1 minus sine x, and you're stuck and you have no idea where you could go next, you can multiply by their conjugates and get a Pythagorean theorem identity, which will make sense in a second, all those big words. So I have 1 minus cos. I can times it by its conjugate, so 1 plus cos x, the top and the bottom. When you multiply by a conjugate, please do not put the two together that are not conjugates. Always leave them in separate brackets. So the bottom we will FOIL, because they're conjugates of each other, but the top, do not put together. I repeat, do not put them together, and I'll show you why in the next step, no, the next 2 steps. So the top I'm going to leave as brackets. Sine x times 1 plus cos x. I am not putting together the two that are not conjugates, and I will show you why in a second, why you do that in the next step. Put together the conjugates, though. So I'm going to get 1 times 1, which is 1. 1 times cos x, which is plus cos x. 1 times negative cos x is negative cos x. What happens when I multiply by conjugates? My middle terms cancel. That's the point of multiplying by conjugate. And then negative cos x times positive cos x is negative cos squared x. So what am I left with? Sine x times 1 plus cos x. I'm not going to put those together because they're not conjugates. And on the bottom, I'm left with 1 minus cos squared x, which is now a Pythagorean theorem identity because I forced myself to get one. What's the Pythagorean theorem identity? It's sine squared x plus cos squared x equals 1, right? So if I subtract that cos squared over, I have sine squared x equals 1 minus cos squared x. What do I now have in my denominator? 1 minus cos squared x. What could I replace it with? Sine squared x. So now I have sine x times 1 plus cos x over sine squared x. Do you see now why I didn't distribute the top? If I distributed the top, I'd have sine x plus sine x cos x. If I had sine x plus sine x cos x, the only way that would be going anywhere is if I had a sine x plus sine x cos x in the bottom, right? Because they're attached by plus signs. And the only way those things, anything that's attached to the plus or minus sign can go away is if they have an exact replica on the top and the bottom. So I'm not going to put them together if it's not the conjugate, because now I can cross this sine x off with one of these. And I'm left with 1 plus cos x over sine x. And you'll see why you actually want to change it when we do proofs right away. Okay, then flip over. Proving identities. So these are the general strategies. Not every single strategy always works, but these are the strategies you could use. So what we're going to be doing is we're going to be proving something like this. We're going to prove that this equals this. They'll give us something like this, prove that this equals this. Or they'll give us one side and say, this equals what? A, B, C, or D, and then they'll give you A, B, C, or D, and you're going to try and figure out which one matches. Okay? Remember, we can prove these by algebra and graphing, or by substitution and graphing. What we could do is we could go y1, y2, and see if they match, right? So if it was a multiple choice, we could go take this side, A, B, C, or D, and match them, correct? Or we could plug in 30 degrees for all of these, right? And then plug in 30 degrees for all the x's in the answers and see which one gets you the same answer. Do it that way. But if it's full out proof like this, you actually have to know how to do it. Okay? So these are our necessary steps. Split the equation into two parts, left-hand side, right-hand side, without the equal sign between them. I always leave the equal sign, but you can ditch it. I like putting a line in between them because that's like an electric fence. Anything on the left-hand side is not crossing anything on the right-hand side. They can't cross over. You can't like add the right-hand side to the left-hand side and put it all over here. You can't do that. When you're proving something, everything on the left-hand side stays on the left, anything on the right-hand side stays on the right, and the equal sign like makes you like an electric fence in between. They cannot cross over. Okay? One rule. 2, look for obvious substitutions using the basic identities. So like the 3 identities, the Pythagorean theorem ones, sine squared theta, cos squared theta equals 1. So whenever I see sine squared or cos squared with a 1, or cotan or tan or secant squared or cosecant squared, any of those squareds with 1s, I look for the Pythagorean theorem one that I could possibly switch it out because it needs to have a +1 or a -1 with it in order for that to even attempt to work. Okay? Or you might be inserting a 1 in its place. 3, simplify the most complicated side with the goal of making it equal to the other side. Sometimes you have to simplify both sides to get them equal to each other. But I always start with the most complicated. So if one side's like really complicated and the other side equals cos x, there's nothing I can do to the cos x. So I'm going to have to work this side down and hope that I can get it to be cos x, right? If necessary, write in terms of sines and cosines. So that's one thing that I always like doing. Write expressions with fractions as single fractions. So if you have like sine x plus cos x, or sine x over cos x plus 1, you're going to want to write that as a whole thing all over cos x, okay? So if you have like a fraction plus something, you want to put that as a full fraction, like we were doing before. Look to divide out common factors, multiply numerators and denominators by the same expression, possibly conjugate if necessary. So if you get that plus sine x, or sine x minus 1, or cos x minus 1, right? Then you want to do the conjugate, or plus 1. So let's try and prove some of these. Sine squared x over cos squared x plus 1 equals secant squared x. This side looks more complicated. I'm going to try and make it one fraction. So I'm going to need to be a denominator of cos squared x. So I'm going to turn this 1 into cos squared x over cos squared x, because that's just 1, right? So I'm going to get sine squared x over cos squared x plus cos squared x over cos squared x equals secant squared x. What I like doing, so I like putting my little line through it, like it's an electric fence, can't cross over. What I like doing is turning secant squared x into 1 over cos squared x myself, but you can leave it as a secant if you want. It doesn't matter. Or you can write it as 1 over cos squared x, because that's what it is. Now, I'm going to get sine squared x plus cos squared x all over cos squared x. Sine squared x plus cos squared x all over cos squared x equals secant squared x. What can I do? If I'm stuck, I go to my formula sheet. What's sine squared x plus cos squared x? Your formula sheet will be your BFF. Trust me for this entire lesson. Yeah, 1. Sine squared x plus cos squared x equals 1. It's your very first Pythagorean theorem identity. So I'm going to get 1 over cos squared x. equals secant squared x. So at this point, I could make them equal to each other. I could go 1 plus cos squared x equals 1 over cos squared x, right? And they would be equal. Or I can make them both be secants. It doesn't matter. You just have to show that they're the exact same. Once I prove left side can equal right side somehow, I'm done. My proof is done. Sometimes there's more than one way to solve the proof out too. So I'm just showing one way. So B is sine squared x plus sine squared x cotan squared x equals what? So there's a hint of factoring below it. So the only thing I could do is I could change some of those sine squared x's into 1 minus cotan squared x, or I could change the cotan squared x into cosecant squared x minus 1. So that's making it more complicated. So what I'm going to try and do is, they both have a sine squared x, and sometimes you have to be able to see and spot that. So you can pull a sine squared x out of both of them. So you're going to get sine squared x as the GCF. Now this is the catch that people mess up. When I take a sine squared x out of sine squared x, what am I left with? 1, not 0. It doesn't just cancel off, which some people do. Sine squared x divided by sine squared x is a 1. Plus, my fence is a little shifted, but that's good. Plus, when I take a sine squared x out of sine squared x cotan squared x, I'm just left with a cotan squared x. And it equals 1. This is why I told you need to know what's on your formula sheet. Because to me, I see 1 plus cotan squared x and I think something. You see that and go, oh no, I don't know what to do. What's 1 plus cotan squared x? Cosecant squared x. So we get sine squared x times cosecant squared x, oops, equals 1. What could I do? I need something to cross off so I get a 1. What's cosecant squared x? Yeah, 1 over sine squared x. C screams sum and difference. Please spot the sum and difference. They're the easiest ones because there's nothing else it could be. This here's a sum and difference. It has one trig, so it's sine, cos, or tan. It's sine in this case. And it has something minus something or something plus something following one of them. So we're going to use the formula. The formula is sine A minus B is sine A cos B minus cos A sine B. Remember the formula is this. Sine A minus B equals sine A cos B minus cos A sine B. And this is A and this is B. I know it's an A. It's confusing, but it's not. It's a B. So we're going to go sine A. A is 270. Cos B, which is actually A, minus cos A, which is 270 degrees, sine B, which is actually A, equals negative cos A. What could I do next? Remember, these have actual answers. What is sine at 270? Negative 1. Minus, what's cos at 270? What's the x at 270? 0. That cancels. And I'm left with negative cos A. Then flip over. Try D. So sine pi minus x is going to be sine pi cos x minus cos pi sine x equals sine x. Sine at pi is the y value at 180, which is 0. So I'm going to get 0 cos x minus cos at pi is -1, so it's minus a minus 1 sine x equals sine x. Those cancel. Minus a minus is actually a plus, so you get sine x. So this is where that conjugate comes in. So I see, prove the following. Cos 1 minus sine x equals 1 plus sine x over cos x. They're all single sines and coses. I can't make anything be sines and coses. Like if I'm stuck and it's like a cosecant, at least I could change that to like a 1 over cos or 1 over sine. Or if it's cotan, I could change it to cos over sine, right? But I'm basically stuck. So pick one of them and multiply by the conjugate. So I could either take this one and multiply it by 1 minus sine x, or I could take this one and multiply it by 1 plus sine x. I'm just picking one of them. I don't pick both and multiply both conjugates. So I'm going to do the left side. So I'm going to multiply this by 1 plus sine x. And I'm keeping the right-hand side the same. When they're not conjugates of each other, remember I told you to not put them together, right? We don't want to put them together. So we're going to get 1 plus sine x times cos x all over 1 times 1, which is 1, plus sine x times 1 is positive sine x, minus sine x times 1 is negative sine x. Sine x times negative sine x is negative sine squared x. Those cancel. And I'm left with 1 plus sine x over cos x here. Here I'm going to get that. I'm not going to change it. I'm not going to put it together. And on the bottom, I have 1 minus sine squared x, right? Here I have 1 minus sine squared x. What can I replace 1 minus sine squared x with? Why do we multiply by the conjugate in the first place? 1 minus sine squared x, that Pythagorean theorem identity, the very top one, sine squared x plus cos squared x equals 1, rearranged. So if I move the sine x over, I'm going to get cos squared x equals 1 minus sine squared x, right? So 1 minus sine squared x is cos squared x. That's why we multiply it by the conjugate. And now is when people start getting happier because they start seeing that they could probably get them to match. This cos squared x, I can take 1x off for 1 cos x off for 1 cos x, and I'm left with with B. You could change things into coses if you want. Then you're going to have fractions. You'll be distributing in fractions. What I'm going to do is I'm going to spot that secants and coses are kind of like opposites of each other, right? Cos is just 1 over, and secant, cos is cos and secant is 1 over cos, right? So if you get a cos multiplied by a secant, it's actually 1. So I see that I can distribute these and see what happens. Secant x times 1 is secant, well, secant theta times 1 is secant theta. Secant theta times cos theta is secant theta cos theta equals 1 plus secant theta. Now I have a secant theta and a secant theta. I need this to be a 1. Well, secant theta is going to stay secant theta because I need it to still be secant theta. Secant theta I can write as 1 over cos theta times cos theta over 1. This would result in cos theta over cos theta, which is just 1. I'm going to get secant theta plus 1. One minus cos squared theta equals cos squared theta tan squared theta. What do you spot? What could you do, possibly? 1 minus cos squared theta is what? Sine squared theta, yes. And then cos squared theta tan squared theta. Okay, we've been halted. What's the only thing I can do? Sine is sine, cos is cos. I could maybe change some sines and coses, but that probably doesn't sound good. What can I do with the tan squared theta? What is tan? Sine over cos. I see a good thing there. So sine squared theta equals cos squared theta times sine squared theta over cos squared theta. Is anyone seeing something cool here? Or at least making you a little happy? So this time we did a little bit on both sides, right? Proved it to work. You try B. A hint to B is secant squared x minus 1 is a Pythagorean theorem identity. If you rearrange the 1 plus tan squared theta equals secant squared, you'll get tan squared theta equals secant squared theta minus 1. So we'll get secant squared x over tan squared x, sorry, equals cosecant squared x. Remember, secant is just 1 over cos, and tan is sine over cos. So I'm going to write them side by side because they're just going to be fractions divided by a fraction, right? So secant squared x is 1 over cos squared x. So secant squared x is this, and it's divided by tan squared x. But instead of writing tan squared x here, I'm going to write sine squared x over cos squared x, because that's what tan is. And I still am left with cosecant, or I could write it as 1 over sine squared x if I wanted to, because that is what cosecant squared x is. So I literally just wrote secant squared x divided by tan squared x, but then I replaced secant squared x as 1 over cos squared, and I replaced tan squared with sine squared over cos squared. So I'm going to get 1 over cos squared x times cos squared x over sine squared x. All right. The cos squared x's cancel, and you're left with 1 over sine squared x. Then flip over and try the next page. If everything cancels off the top, does that just mean the top goes away and vanishes for life? What is it still? It's a 1. B, whenever you have a fraction and it's not completely together, you have two fractions or whatever, I always put them together. So I'm going to times this one by cos x over cos x. To get a common denominator. And I'm going to times this one by sine x. What's cos x times a secant x always? 1. Because what's secant x? 1 over cos. So what's cos times 1 over cos? 1. So when you multiply two reciprocal identities together, they get you 1. What's 1 minus sine squared equal to? Cos squared x. It's just that formula rearranged. With these ones, cos 2x has 3 options. Okay, so that's the last one I'm going to fill in. It has 3 options. Sine 2x has 1 option. So I'm going to fill it in there. So I get 1 plus I don't know. So I'm just going to leave that be what it is because I want to see what the heck the rest is before I even try and fill it in because it's pretty ugly. Sine 2x is 2 sine x cos x. It's off your formula sheet. There's only one thing that sine 2x can equal, so I can fill that one in, and it's no big deal. And then cotan is cos over sine, so I'm just going to write that. You could leave it as cotan, and you'd be absolutely fine. I need to fill something in here so that I can get a cos x on the top. I need to get this cos x to go away. So I'm going to need technically cos squared x on the top somewhere, right? So I can get this cos to go, yeah. This cos to go away and still have a cos up here. I need to get the 2 to go away. So my 3 options are cos squared x minus sine squared x. So if I add a cos squared x minus sine squared x here, is that going to get me any? No. I have 2 cos squared x minus 1. Is that going to help me? 2 cos squared x minus 1. Remember I said I need at least 2 cos squared x's up here? Because if I have 1 cos squared x, I can cross this one off and I have to still be left with 1. And so I could use the sine squared one, but it's not going to help me because I'm going to end up with a sine squared up here. The 1 and the minus 1 cancel. So I'm left with 2 cos squared x over 2 sine x cos x. This is the last one we'll do. Sine x plus cos x squared means you have 2 sine x plus cos x's. Don't tell me that's sine squared x plus cos squared x, because it's not. This means you have 2 of them. Technically on the top. So on the top, I can FOIL that. I'll get sine times sine, which is sine squared x. Sine x times cos x is plus sine x cos x. Inside is plus sine x cos x. And then last is cos squared x. Over sine 2x. There's only one formula I can fill in for it, right? 2 sine x cos x. Whenever I see sine 2x, I'm going to replace it with 2 sine x cos x. It's the only formula I have for sine 2x. I'm just going to leave this side for now, just so I don't overwhelm you. This is really not that fun. Okay. Please pay close attention. This is a 1 sine x cos x. This is a 1 sine x cos x. So that's technically 2 sine x cos x, right? Like having a 1xy plus a 1xy, it's 2xy. So it's 2 sine x cos x. And then I'm going to put the sine squared x plus the cos squared x together. Whenever you have a sine squared x and a cos squared x apart, like these ones are, I always put them together. Because what is sine squared x plus cos squared x? 1. So if ever you have a sine squared x plus cos squared x randomly apart and you can put them together, sine squared x plus cos squared x equals 1. So I can just cross these out and they become a 1. So I technically have 2 sine x cos x plus 1 over 2 sine x cos x. These are attached by a plus sign. They're not. You can't just cancel those 2 off and have a 1 miraculously. Okay? You can't do that. Don't do that. Cosecant 2x isn't on the formula sheet, right? But cosecant is just 1 over sine, correct? This is like the ugliest of the ugly you could get. So if you're freaking out, this is like the ugliest of the ugly. Okay. So it's going to be 1 plus 1 over sine 2x, right? Because sine 2x I have in my formula sheet, but I don't have cos 2x. So I can go 1 plus 1 over 2 sine x cos x, because whenever I have sine 2x, I replace it with sine x cos x. I have two fractions that aren't together, so I want to put them together by common denominator. So I'm going to make this 1 be 2 sine x cos x over 2 sine x cos x. This side just stays the way it is because there's nothing I can do with it. So I'm going to change this 1 to 2 sine x cos x over 2 sine x cos x. So I can get a denominator. That's common. And now you'll see that they're actually going to be the same. This side just rewrite. This whole side could be over. And on the top I have 2 sine x cos x plus 1. So what do I want you to work on tonight? The hand-in. I want you to work on the hand-in. On the hand-in, the last page and the first question on the first page are proofs. So do those for practice for now. That way, if you need to at lunch tomorrow, you can maybe ask for hints if you're stuck or something like that. Do your hand-in. You don't need to print off the hand-in. You can write your answers on lined paper and hand it to me that way. I don't really care. Just make sure you number them. Don't like randomly go, I don't know. Please put some order into it. Okay. There is homework for this. It's on the next page, but I just want the hand-in done tonight. So if you have extra time on your hands, you can start working on the